This lecture begins the viscosity series of lectures for polymer rheology and processing, or low Deborah number measurements. This is viscosity, video 1. To give you a little bit of an introduction to viscosity, viscosity is traditionally regarded as the most important material property when dealing with lower molecular weight or lower sort of polymeric materials. Any study regarding the knowledge of a material generally turns to viscosity first. And there's detailed attention paid to steady shear viscosity. So, to revisit Newton's postulate, shear stress is related to the velocity gradient through this equation here. So, shear stress equals viscosity times the shear rate or the strain of the material, where again this term is the shear viscosity. This gives you the idea of some familiar materials at room temperature. Glass itself is a very slow flowing liquid, but it is a liquid nonetheless, and its approximate viscosity in Pascal seconds is 10 to the 40. So very thick, but still flowing. Molten glass, obviously not at 20 degrees Celsius, is about 10 to the 12. Most molten polymers, again not at room temperature, are about 10 to the 3. Things like syrup or honey, glycerol tend to be about on similar orders of magnitude. Olive oil, bicycle oil, water, and air are quite a lot lower in viscosity than, say, something like glycerol or honey. These examples all exhibit Newtonian behavior. And in this case, viscosity is independent of shear rate for the shear rates of particular interest of these systems that made up this table. So, interpretation of viscosity. For Newtonian liquids, viscosity is sometimes called coefficient of viscosity, but of course most commonly we refer to it simply as viscosity. In reality, viscosity is not a coefficient of shear rate, it is a function of the shear rate. And so eta times gamma is defined as shear viscosity. Sometimes this is apparent viscosity, sometimes this is shear dependent viscosity, but it is a function of shear rate as opposed to a coefficient. There are physical ranges of variables that affect viscosity. Viscosity of real materials can be significantly affected by a number of these factors, and these include shear rate, temperature, pressure, and time of shearing. And it's important to review the way viscosity depends on such variables. And so this gives you kind of a brief overview of practical ranges. So if you're looking at, say, a sedimentation of fine powder in a liquid, the shear rates you're looking at are 10 to the negative 6 to 10 to the negative 4 in things like medicine and paint. If you're looking at polymers in an extruder, you're looking at 10 to the 0 to 10 to the 2 for typical polymers. If you're looking at things like lubrication for something like in an engine, you're looking at 10 to the 3 to the 10 to the 7 inverse seconds for shear rates. And so there are a variety of different processes and have a variety of practical shear rate ranges in their use. For the most part, for industrial applications, the temperature range of a material is limited by the material itself. Aqueous systems, of course, are limited by freezing and thawing and freezing of water, so 0 Celsius to 100 Celsius. Lubricating oils and greases, negative 50 to up to 300. Polymer melts, you have to first melt the polymer, so you need to get it up usually above 150 Celsius to up to 300. And if you're dealing with molten glass, you're dealing with at least 500 degrees Celsius. When you're dealing with a laboratory viscometer, you can test from reasonably negative 50 to 150. So not all of these materials can be tested in a laboratory type viscometer. Typically, an external temperature control is necessary because temperature is a factor when determining viscosity. These include circulating fluid or immersion baths, or higher temperatures require air baths for this to be accomplished. The viscosity of Newtonian liquids decreases with temperature, and according to the Arrhenius relationship shown here, so viscosity equals liquid constants A times E to the B, which is also a liquid constant, times the absolute temperature. For Newtonian liquids in general, the greater the viscosity, the stronger the temperature dependence. Strong temperature dependence of viscosity requires good temperature control. This always has to be specified when you're talking about the viscosity of material. The temperature always has to be specified. So, for example, for water, the temperature sensitivity of water is 3% per degree Celsius at room temperature. So to have plus or minus 1% accuracy requires that a sample be maintained at plus or minus 0.3 degrees Celsius. So it's very, very critical that temperature is controlled. And again, higher viscosity liquids in water, which are most things, have stronger temperature dependence than this. So even greater control has to be taken to maintain temperature when measuring viscosity. Temperature control does not just mean thermostat control. My thermostat on that water bath has been set to 20 all day. It's perfect. You have shearing itself. Oftentimes we're doing a shear rate, so shearing itself generates heat. And therefore shearing alone may not change the temperature enough to decrease viscosity, but you have to be aware of that. So steps have to be taken to remove heat generated by shear. And so you have a sort of relationship here. Energy dissipation rate divided by the shear liquid volume equals shear stress times shear rate, which equals viscosity times the cube of the shear rate. So higher the viscosity, the more heat that is generated. The rate of heat extraction is also important. It depends on two things. The kind of apparatus. There's one where a test liquid flows through and out of the apparatus, and this is slits and capillaries, and then liquid, and in this case liquid flow convects away. Type 2 is a test liquid is permanently contained within the apparatus, and this is concentric cylinder and cone and plate viscometer. Conduction of heat is only to the surface, and that's the only significant transfer event. The second thing you have to pay attention to is the dimension of the viscometer. Slits and capillaries have a channel width that's controlling this parameter, and then concentric cylinders like cone and plate viscometers, the gap width within those is very important. And desirable gap widths tend to be as small as possible. When looking at viscosity variation with pressure, the viscosity of liquids increases exponentially with isotropic pressure. Water below 30 degrees Celsius is the only exception. In this case, viscosity first decreases, then eventually increases exponentially. Changes are quite small for pressures differing from atmospheric pressure to about 1 bar, and generally, for most purposes, pressure is ignored by most viscometer users. But there are situations in which you just can't ignore the effect of pressure, and one of these is the oil industry. This requires viscosity measurements of lubricants and drilling fields at elevated pressures. The pressures experienced by the lubricants in gears can exceed 1 gigapascal, and oil drilling muds operate at a depth where pressure is about 20 megapascals. So in this case, you do have to take pressure into account when testing lubricants and drilling fluids. This shows a plot of the variation, the log of viscosity by isotropic pressure. Curve A is 2-ethyl hexyl sebacate, and then B is mineral oil at 100 degrees Celsius, and then mineral oil at 38 degrees Celsius. So as you increase the thixotropic pressure, you get an increase in viscosity that is for di-2-ethyl hexyl sebacate, and for mineral oil you can see it's even higher. So there are variations in pressure with pressure, and it's something that does have to be taken into account if your application is going to be exposed to pressures above atmospheric pressure. So when we are talking about low Deborah number materials, we are talking about materials where the Deborah number is significantly below 1, and this is typical fluids. Molecular motion in the case of these is sufficient for the microstructure to remain at or close to the low energy conformation, and the work that is done is continually dissipated. When the stress rate that we apply is constant, deformation will occur at a constant rate. This results in a linear relationship between shear stress and shear rate, and then that sloping line is the viscosity that we've been discussing. The reciprocal of viscosity is considered fluidity. And when we have this linear relationship between shear stress and shear rate, this indicates that we're dealing with a Newtonian fluid. Shown here is a rheogram of water. Here we have the relationship, so shear stress, viscosity, and shear rate or strain. And you can see this demonstrates very typical Newtonian behavior, a linear relationship between stress and shear rate, and again, we have to specify our temperature. So the slope of this line gives a viscosity value of 8.84 times 10 to the negative 4 Pascal seconds. And this is in line with previous slides. This is a rheogram of a Bingham fluid. This does have a linear relationship between shear stress and shear rate, that being viscosity, but this also has a yield stress. And here we have a viscosity value of 5.3 times 10 to the negative 3 Pascal seconds. That is only reached, however, and in this case I should point out, in this case stress is on the x-axis and shear rate is on the y-axis. This is inverse of the previous. In this case you have a yield stress to overcome before it behaves as a Newtonian liquid, and that is the definition of a Bingham fluid. So after you overcome this shear stress, this yield stress, then it behaves linearly and gives you a nice slope that is that is the viscosity. When we're talking about the microstructural impact on the Deborah number, the reciprocal of the shear rate is the characteristic time for our experiment. As long as the microstructure can reorganize in a shorter time scale than our characteristic time for our experiment, the value of the Deborah number is less than 1. And again, this is typical fluid behavior. The structure will remain in a conformation that is close to equilibrium if we're dealing with a low Deborah number. Thus concludes low Deborah number materials, viscosity, video 1.